So, good morning, everybody. When we found out there was a polling system here, we thought, wow, what a wonderful opportunity to have this group of specialists here and ask some questions that are really sometimes on our mind. And one of the first questions that we just like to bring to your attention are, when you talk about closing efforts in your company or in your group, in your environment, what are you really talking about? Are you talking about how fast the door is closing, the minimal closing speed? You are more talking about an energy, like how many joules do I need to close this door? Is it more a force measurement for you, or are you the successful ones where you say, we have no issues with our doors, everything is fine, we don't need to measure them? So I would kindly invite you to, use that little machine and cast your vote, and we're all excited to see what comes out of it. Five, four. Okay. Well, 9%, I'd like to meet those people. And then, so we have a relative distribution with the winner, let's say energy is the most common one. A few forces, a few speed, that's very interesting. It's of course part of our profession to study all these metrics, and it's not unexpected, but nice to know. Another question that maybe might make you think a little further is, if you evaluate your closing efforts, would you do it from the door fully open, or your first detent, or maybe just that last moment of impact, right? Or you just say, hey, I just want to check that kind of that seal and latch effect, right? And then again, those 9%, feel free to press D again. There's no issues with our doors. Okay, again, the results of the 9% are consistent. That's the proof of concept that the voting works. And then again, about an equally distribution between the different positions, right? So that's also, again, very useful statistical information there. And then the last question that I want to ask the public, again, also to make people think a little bit outside the box. Over the last days, over the last presentations, a lot of people thought about weight reduction. They said, oh, great, we saved weight, right? I appreciate the effort that went into that. Now, I do want to ask the question, if you look at weight reduction, have you ever considered the inertia of the door? Inertia is Maastrichtheid, and it's basically the weight distribution in the door, right? Have you considered saying, I want to maintain the current inertia of my steel door? No, I have considered to reduce the inertia as well. I have not considered it at all. Or yes, I had a brilliant idea, but nobody wanted to listen to me, right? So please feel free to identify with one of those four choices. Okay, so we have a winner. They have considered to reduce the inertia, not considered and the 8%, again, the brave people that want to stand up, but okay. So this is very, very interesting information. I will certainly address that also later during the presentation, these outcomes a little bit, because my real purpose of this is, at the end of the presentation, I hope I can bring along some questions that make you think maybe differently about your doors. So I'll be talking a little bit about the measurement of closing efforts of door dynamics, a little bit about the energy aspect, and then of course I want to spend the necessary time on a few practical examples that we have established over the course of time, and to finalize of course with a conclusion. So a question that is on everybody's mind, and it's probably a fraction of those here on the screen, is what is a good door, right? We have about 200 professionals here. If I would ask everybody, what do you think is a good door? I think some people might mean the same thing, but they'll probably use different words. And there is, I'm curious to see if there's a standard among everybody. Say, yes, this is a good door, but as soon as it's 2.9, we consider it bad, right? I would be delighted but surprised if that would be the answer, right? So you have all these questions that I'm sure have been asked in your organization, and so our strive at EZ Metrology is to provide a solution that allows you to answer these questions in a scientific way, where you say, this is a method, we obtain this value, we like it or we don't. And in the scope of this presentation, we do want to focus on the functionality of the door. Not the component testing, we'll leave that for another chapter, another moment, but we want to test the full functionality, how your customer experiences the door. And of course, we do that by measuring on the fully assembled car, right? Completely finished, everything in place. Also, we want to use a systematic method, right? We want to make sure we always do the same. If we evaluate different vehicles, there is no, we want to limit any user influences, methods, setups, and so forth. And then, of course, we want to do it really fast, right? We gain information from having a larger sample size. Because if we pick the ugly duckling to do the study on, it really gives us a bad impression of the whole process, right? So we want to be fast, and that's why we've been using our EZ Slam technology that's been developed in-house over the last 10 years, and that really does a little bit everything what we wanted to do. A lot of people might or are familiar with EZ Slam already. They have one or more within their organization. For those who are not familiar with it, it's basically a system that has a multitude of sensors built in, integrated from load cells, motion sensors, pressure sensors, kind of high-speed cameras, everything together. And what we do with that, we execute a number of tests, standard tests. We do just a slam test, we do a couple of slam, we push the door close, we go over the door check system to measure your force profile. So it's a standard set of tests, and on top of that, the algorithms that are behind it will take that information and just process it always in the same way. And that results then in what we call a DNA of the door. We say, look, we have a DNA profile, we know the minimal closing speed, energy, hinge angle, peak pressure, and so on and so on. All the characteristics that are important for a door to function. Now, a little bit to the orchestra from yesterday morning. We have so many different things to handle, right? We have a zoo of effects and phenomena that needs to be characterized, right? We can have user input. You might consider that in Newton. How hard are you pushing? We can talk about speed, meters per second. We can have the hinge tip, how many degrees that might be. We have friction, pressure. We have all these different things. And we can't compare that. I Googled, there is no conversion from meters per second to degrees. It doesn't exist, right? So we have to rely on other things. And that's when we fall onto energy. right? We said, well, that user input is really mechanical energy. And from the physics class a couple of years back, I remember energy is basically my force of the user over the course, over the travel. That gives me my energy. And speed, instead of meter per second, I can use energy as kinetic energy. I just figure out the angular speed and the inertia, and I got my energy. Hinge inclination. Back in the memory, they call it potential energy. It's the mass of the door, how high did it go, and then we have our gravity behind it. That's potential energy. And little by little, we transform everything into energy. Friction over the hinge or over the check is also force and displacement. The pressure peak in the cabin, guess what? Pressure times an area times displacement is also energy again. The seal compression, right? If you look at a seal compression curve, this is Y versus force. I know we talk about closing efforts, so many newtons. It's very nice, but I prefer compression energy, that green surface. And so in the end, we have the whole range of metrics, whole range of phenomena expressed in joule. And when everything in joule, we have one basket full of apples, now we can start the game. You say, what do we have? And so we've chosen 3 examples that we want to address based on this energy measurement. Right? Energy balance. A balance refers to the fact that with the door, unfortunately, there's only really 2 actions. You want to open it or close it. That's pretty much our life now, right? And in that balance, there are things that provide energy, and there are things that take energy. And of course, they have to match. Energy cannot just disappear in nowhere. So we can look at the measurement, and I want to insist that these are not simulations, these are measurements. We can take this car, 20 minutes later, we have all these results. There's no simulation involved, right? What do we see when we open the door? We can say, oh, we measured we need 30 joules or 29.6 joules to open this. And there is no magic. The user that is either inside the car or outside has to provide that energy. And then we can say, okay, why do we need 29 joules? Well, we have the answer. Guess what? About 52% of that action, of that energy, has gone into friction. Just turning the hinges, moving over the check, that's 50% of your energy. That's a little bit lost, or completely lost, to be honest. Now, there's other aspects. Because the door inclination is such, you push the door uphill, that's going to cost you energy. Namely, in this example, 40% of your energy. Now, we know that's interesting, because later when we have to close it, that door will go downhill and provide us energy to close. And the third parameter here is a door check. We can design a door check that returns energy when you close it, a high energy door check. It's really nice, but not when you open it. When you open it, you have to pay that price. You have to push the door check in its active position. So that's our other 8% in this example. So it gives us a good overview on what we have in store. And then, of course, the million-dollar question, what if we close? Well, let's see, to close the door, you need 21 joule. Fact. Now, we have good news. Remember when you opened the door, you pushed it uphill? Well, now it's coming downhill. So from this 21 joule that you have to provide, actually in this example, about 50% is provided by gravity. The sheer effect of going downhill will give you already 10 joules. Then the check system that we compressed when we opened the door is also returning some energy. So when I manipulate that door, I really experience only about 30% of that. I experience 21, 30%, around 7 joules. That's what I feel. And that's nice to know. And then, of course, somebody in the room is going to say, why do we need 21 joules? Well, good, we have the answer, right? We needed that 25 joules to, and here again, in this particular example, 70% of your energy is already gone in friction again. Your hinges and check took 70% of your energy. Means by the time the door is even considering touching a seal, 70% of its energy is already gone. And then we have everything else what happens, the seal compression. We have to push the air out of the cabin. We have to push the air out of the seals and the seal environment. That's all the other 30% pretty much. And one of the questions, right, that come to my mind is regarding that weight reduction, right? If you reduce the weight of a door, guess what happens to this one? That gravity that you get from the energy that you would get from gravity reduces. And there is no magic. Who's going to pay for it? The user. So you're going to redistribute this 5732 to maybe 40, 50, right? And unfortunately, there's another effect that I'm sure you might have seen in some occasions. If you have a lighter door, to provide the necessary amount of energy, you gotta travel a little bit faster. And if you go a little bit faster, guess who doesn't like that? The air. The air in your seals, the air in your cabin, they're gonna fight you. So not only have you, with a lighter door, not only will you have to provide more energy, because gravity doesn't help you anymore, you get an extra special bonus penalty from the air that doesn't want to go anywhere. So you're gonna, these 19 and 7%, the cabin and the seal air, they're gonna grow. And if this pie grows, guess what? This one has to grow with it. And again, nobody else is providing it except for the user. So that's, that's maybe interesting information to observe on a door system, right? I would like to bring back the question of inertia of the door. If you reduce the inertia, you're going to have to make it travel even faster, right? If you can increase the inertia of a door, so put the weight away from your hinges, you're going to decrease that speed of the door. And with decreasing the speed of the door, you get, the air is on your side. So these are some thoughts I want to put into your mind so you can at least reflect on it and maybe leave this presentation with some thoughts to say, I never thought of this before. Another interesting new analysis that we've been doing is what we call sensitivity, right? I visited many plants on this planet, and on occasion I see at the end of the line people adjusting the door, right? They have these white gloves on, look at the door, take tweezers to adjust the door or any other tools that they have available, and they're going to adjust it mostly for flush and gap, right? It's very nice, but careful. Somebody's watching. You're closing energy. You're playing with that. And in unfortunate cases, you might be playing with fire, right? What we do is we will say, hey, yes, we had 21 joule closing energy as it is now. We can, based on our measurements, decide if you move the striker in 0.5 millimeter, your closing energy will go up by from like 22 in this example to 24 joules. If you move it out 0.5 millimeter, you're going to drop by a joule. And this type of metric, so here, by that simple operation, don't expect anything else then, well, I'll have variation on my closing energy from 21 to 24 joules. If you limit that adjustment to only 0.5 millimeter, right? This becomes a fact that you have to work with. If you like it, great. If you don't like it, you might have to consider that. And because measuring doors is all we do, we have a vast collection of data in our database. And if we look at this type of sensitivity over a wide range of vehicles, I didn't specify the vehicles to leave that open for discussion and guessing, right? But just by moving that striker 0.5 millimeter, you have a few lucky ones where the energy doesn't change a lot. It's a very linear, very flat curve. For the few unlucky ones, you can see as much as 5, 6, even up to 10 joules difference just by changing that striker. The 10 joules is, of course, you're hitting a wall. You moved it inside, and you hit bumpers, you hit everything that NVH people did to your door, right? And it won't close anymore, or it takes a huge amount of energy, right? That's very interesting information, but it allows you to evaluate that adjustment process and say, maybe we should not do that, or maybe we should be a little bit more careful about adjusting this or that. And then a last, more progressive representation of energy is a little bit the distribution of it. This graph, if I have to explain it relatively quickly, is what we give, and this is how it's used, right? And if I give only 5 joules, so very little energy, guess the door is not even going to close. It's going to go halfway, and friction will have consumed everything. Everything I gave, friction took it and said, the door will stop here. If I start providing more and more energy, at this particular point, I start touching my seals, right? And so all the energy I gave, that 12 joules, is consumed by friction and what we call drag, which is a little bit the air friction during the travel, right? So when I give 12 joules, we just reach that point of compressing a seal. And then I go down further, I give more and more energy, and little by little, we compress the seals a little bit more. We're not closed yet, but we start pushing out the air. We're not closed yet. We go further and further until a particular point where the door closes. And we're happy. That's where we are now. If I provide more energy, that's perfectly fine, perfectly normal, right? You have a bad weekend, you close the door Monday morning, you're going to provide more energy than the minimal energy. That's fine. The energy will be redistributed in a different way. Something will absorb that energy. So that's the evolution. Now, where we're going with this graph is that you see that if you have one component, right, could be the seal compression, or could be the air bind, the air in the seals. If that would increase a little bit, that whole second line would shift to the left, or right, right, let's say. We shift to the right, and by shifting to the right, actually, you get also more of everything else. So if you would increase your seal compression a little bit, that's okay, but you're also going to increase your air bind. And because you have to slam faster, you're also going to increase your cabin pressure. And so you have all these compounding effects, right, that we're sometimes struggling with because it's just a waterfall of everything is going bad. Or not as good, sorry. An example that everything I should be able to imagine, right? We have cabin air, the air in the cabin that is enclosed in the cabin. If we say, hey, we managed to reduce it by 1 joule, that's good. You know what? Because of this, I can close the door slower, and the air in my seals have more time to escape. So there also I'm going to gain a little bit. Because I'm traveling slower with the door, I'm also going to gain on what we call drag. It's going to be less air resistance throughout the travel. And then the final one is friction. Friction, a little bit like your ABS system, there's a difference between dynamic friction and static friction. If you go slower, you will experience a little bit more friction. So that's a little bit against us. That brings it up again. But the net results from working on a 1 joule on my cabin actually results in a 1.4 joule in my overall closing effort, closing energy. And that's interesting to know, right? Here on those graphs, we can read the different components. We can say, oh, if I work on friction, if I gain 1 joule, I get 1 joule pretty much. If I work on cabin air, if I gain 1 joule in my cabin air, my overall benefit will be 40% more, is 1.4. If I can gain on seal air evacuation, let's put it that way, if I gain 1 joule there, my overall gain is going to be 2.2, more than double. If I gain 1 joule on just static closing effort, right, I also gain just about the same, just 1 joule. So you can, with this type of evaluation, you can relatively quickly pick your battles, see what is challenging and see what will give you the highest chance of succeeding a certain goal. And so this brings me to the conclusion, a little bit more generic again. All these metrics, what we're really trying to achieve is to put numbers to this subjective feel of, I like this door, I don't like this door, right? We get these numbers, and with these numbers, I'm sure you can imagine applications where you say, oh, I don't like this one, I did like that one. My plant manager liked this door, let me get that signature and see what it's like, right? So those numbers allow all these processes to work in a scientific way and make you able to say, hey, these are my goals, I met my goals. Okay, so I'd like to conclude this presentation. I want to thank you, of course, for your attention. I do want to point out we are 10 years in existence, and we have compiled a small booklet with a little bit our thoughts on closings and measurements of the doors, right? We have it at our booth. Feel free to stop by. We'll be happy to give you even a signed copy if you want. So, yeah, please feel free to stop by and ask any questions. Thank you.
I need to switch this on. It is. Thank you very much for, I think, a very interesting presentation.
You're
I would
welcome.
also like our tradition of our little speaker's gift already.
Thank you very much. Thank you very much.
Thank you. I think that's really a very interesting way of thinking. I would like to ask as a first question maybe, what is the status of, say, using this thinking in the automotive industry? What is your experience? Are there applications, are there OEM working like that already, to your experience?
Yes, I think the mainstream is going this way. People are looking for metrics to evaluate, did it improve, did it get better, or was it in vain? So there is a need and a quest for these, for these type of objective values, right? But
I hear a lot of talk already, and of course there's a possibility for you all also to ask questions right now to Tom van Esch. Are there questions or remarks from the audience? Yes, please, in the back.
Thank you very much for your presentation. I think it's a very good and a very interesting way to measure the energy for the door. And you have done a lot of investigation for that. But here I have one question. How to calibrate the meter? I mean that how do you know that you can get the right number when you measure the energy? Thank you.
And I'm sorry, what number are you looking for?
I mean that how to calibrate the meter when you measure the energy. How do you know that you have got the right number?
We'll have to go into detail into the whole measurement technology. We see with EZ Slam, we collect all this data from different tests, right? And eventually the door is a little bit like a puzzle. Every test will give us a piece of the puzzle, right? And in the end, because we know the behavior, the dynamic behavior with speed and the static behavior of closing, we can determine that optimal, that minimal condition, right? And yeah, we worked a lot. It's 10 years of development pretty much in trying to make this system as user independent as possible. We don't want the user to say, okay, that's it for today, that's my minimum, I'm happy. No, we want to avoid that. We want to be reproducible, repeatable, where the user does not have an influence on the outcome.
Do we have another question from the audience? Let me look around. Okay. Can I perhaps ask one further question myself? Your presentation triggered just one thought. Is it possible to use this kind of analysis you're taking also to help in, say, predicting or analyzing door noise or NVH behavior?
Mm-hmm.
Is that somehow possible to offer and help in simulating that?
Yes, absolutely. You have, I mean, there's two aspects. You can talk about the simulation.
Yeah.
And I know many of us have simulation packages that have been established based on experience, and that's fine. And we see a lot of customers using this to feed back into their simulation package, to really tweak it. And I mean, it's not done. Simulations has to be more and more accurate. We provide those measurements to double check their simulation and say, hey, no, we underestimated that component, or we underestimated this, right? And with respect to door noise, it's actually a very positive feedback from the noise NVH department, where they say, oh, we can analyze noise, that's very good, but it's also very interesting to get that complete dynamics of the door. How does it close? What is that last moment of deceleration? What are we hitting, the forces that are at play? So for noise analysis, it gives also very good feedback on what you're dealing with. How heavy the door is,
That's
how
thinking, yeah.
strong the seals are. Okay?
Okay.
Thank you very much.
No questions further from the audience? I don't see it. Then indeed, thank you very much, Tom, once
Thank
more
you.
for an excellent presentation. Thank you.
Thank you.